The beginnings of elementary particle physics. We will study the beginnings of elementary particle physics in this second elementary particle physics video, because to understand our present-day view of elementary particles, it is necessary to understand the ideas leading up to their formulation. We begin describing the meson theory of nuclear forces. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. One of the biggest challenges for physicists in the 1930s and 1940s was to explain how the nucleus of an atom could be held together despite the electromagnetic repulsion of the protons within it. We can consider elementary particle physics have begun in 1935 when the Japanese physicist Hideki Yukawa predicted the existence of a new particle that would in some way mediate the strong nuclear force. He developed an idea based on a very simple model. A molecule of hydrogen gas is bound together by the influence of two electrons, which are passed back and forth between them. Even simpler is the hydrogen molecule ion, which consists of an electron orbiting about two protons. The shared electron fills their only energy level, giving them the most stable arrangement of electrons. Then, in 1935, Yukawa proposed and predicted the existence of a new particle that would in some way mediate the strong nuclear force. Yukawa called this predicted particle a meson, meaning medium mass. The figure below is a Feynman diagram illustrating proton-neutron binding via pi-meson exchange. This exchange is the source of the strong nuclear force. Protons and neutrons continuously emit and reabsorb pi-meson. If this interaction is mediated by exchange particles, where does the energy to create the mesons come from? For a proton to emit a meson would require energy to make the meson's mass, which, coming from nowhere, would violate the conservation of energy. The uncertainty principle helps us to solve this question. A state that exists for a short time has an uncertainty in its energy, such that. So the uncertainty principle allows no conservation of energy if it occurs only for a very short time. This uncertainty permits the creation of a particle with energy provided that it lives no longer than the time given by the uncertainty principle. A particle that can exist for a short time because of this energy uncertainty is called a virtual particle. Let's look at the Feynman diagram below to explain the process of exchanging virtual particles better. There are several stages. Before T sub 1, proton and neutron approach each other just like classical particles. At T sub 1, the proton emits a virtual particle to the right, let us say, in which case, by momentum conservation, it will recoil to the left. At some time T sub 2, given by uncertainty principle, the neutron absorbs the virtual particle in such a way that two things happen. The neutron recoils to the right because of the momentum it picks up from the virtual particle, and the total energy of the two mesons is equal to what it was before the intermediate virtual state. The total energy of the two nucleons before and after the intermediate state is the same. We would not have violated any rule of physics. We know that such a sequence is impossible from the point of view of classical physics, but it only violates energy conservation for a time given by the Heisenberg uncertainty principle. Yukawa argued that the meson must live to a time long enough to travel a distance comparable to the range of the nuclear force. If we assume that the meson travels at relativistic speed, close to the speed of light, and travels about half the range of the nuclear force, its lifetime must be about. Yukawa used this time to calculate the minimum necessary uncertainty in energy in this process, and then the mass of these virtual particles. To estimate the mass of the meson, Yukawa used this time into the uncertainty principle equation. The mass of the predicted meson roughly is about 250 times the electron mass, and Yukawa postulated that an as yet undiscovered particle with this mass serves as the messenger for the nuclear force. A year later, Carl Anderson and his colleague Seth Nethermeyer discovered in cosmic radiation two new particles, now called muons. The negative muon has charge equal to that of the electron, and its particle, the positive mu, has a positive charge with equal magnitude. The two particles have equal mass, about 207 times the electron mass. But it soon became clear that muons were not Yukawa's particles because they interacted with nuclei only very weakly. In 1947, a family of three particles, called mesons or pions, were discovered in cosmic rays by Latz, Powell, and Occhialini. Their charges are positive electron, negative electron, and zero, and their masses are about 270 times the electron mass. The pions interact strongly with nuclei, and they are the particles predicted by Yukawa. Yukawa's theory of pion exchange as carrier of the strong force was very important. However, as physics continued to advance, it revealed that the mesons were just the tip of the iceberg. Yukawa's theory has been superseded by quantum chromodynamics, in which protons, neutrons, and other strongly interacting particles are made up of basic entities called quarks. But the basic idea that force can be understood as the exchange of particles remains valid. All particles in nature are subject to four fundamental forces: the strong, electromagnetic, weak, and gravitational force. These fundamental forces and their exchange particles are given in the table below. The electromagnetic force is carried by the photon and is responsible for the binding of atoms and molecules. It's a long-range force that decreases in strength as the inverse square of the separation between interacting particles. The strong force is carried by gluons. This force is responsible for the tight binding of quarks to form neutrons and protons, and for the nuclear binding of neutrons and protons into nuclei. The weak force is a short-range nuclear force that governs the decay of unstable subatomic particles and underlies some forms of radioactivity. The particles that transmit the weak force are referred to as W positive, W negative, and Z0. They were detected in 1983. Finally, The gravitational force is a long-range force. The carrier of the gravitational force has been named the graviton, but its existence has not been detected, and it may not be detectable. The gravitational force is by far the weakest of all the fundamental forces, and its effect on elementary particles is negligible. We have just seen that force can be mediated by the exchange of virtual particles, and it reflects the strange behavior of quantum particles, which bears no resemblance to the action of the physical objects in classical physics. This weird behavior of quantum particles can be easily represented using a simple illustration called the Feynman diagram. Feynman diagrams were first introduced by Richard Feynman in 1948. The detailed rules for drawing Feynman diagrams are directly related to the equations of quantum electrodynamics and are beyond the scope of our discussion here. However, a brief description of a simplified version of the diagrams and a few basic rules will be ample for our use in illustrating the phenomena of interest in these and future videos. In particle physics, Feynman diagrams are two-dimensional space-time graphs, and they are pictorial ways of representing the interactions of quantum particles. Feynman realized that the interactions of particles on the quantum scale could be represented on paper by a series of arrows and wavy lines following a set of simple rules. Lines with arrows represent particles and the direction of their travel, and particles have arrows against the direction of time. Exchange particles are represented by wavy lines. There is not a clear convention on which axis is time and space. Particle physicists often draw diagrams with time moving horizontally from left to right, and vertical direction representing space, in this case c times t. Interactions occur at the vertices, two straight lines connected to a third wavy line. Draw a Feynman diagram for the reactions below. This interaction represents electron-electron scattering. Let's draw a Feynman diagram for this reaction. This diagram is read like this. Starting on the left, two electrons approach each other. The electrons are represented by lines with arrows in the direction of time. As they get close, momentum and energy get transferred from one to the other, carried by a photon represented by a wavy line, and then the electrons scatter away from each other. Note that Feynman diagrams tell us nothing about the actual paths of the two particles. The angles in the diagrams have no significance. This equation represents the interaction that occurs when an atomic electron is absorbed by a proton in the nucleus and is called electron capture, and this interaction occurs via the weak interaction and is mediated by a W positive boson. The electron reacts with one of the nuclear protons, changing a nuclear proton to a neutron and simultaneously causes the emission of an electron neutrino. Electron capture produces a daughter nucleus with an atomic number of 1 less than the parent nucleus. The interaction that occurs when a free neutron or one in an unstable nucleus emits a beta particle is called beta minus decay, and this interaction occurs via the weak interaction and is mediated by a W minus boson. In this case, a neutron decays into a proton and a W minus exchange particle, which subsequently decays into an electron and an anti-electron neutrino. The end result is that a neutron has turned into a proton. Electron-positron annihilation is the process in which a positron collides with an electron, resulting in the annihilation of both particles. Electrons are beta particles, and positrons, or beta plus particles, are of equal mass but opposite charge. In this interaction, their masses are converted to two annihilation gamma photons. In pair production, a high-energy photon interacts with the large nucleus of an atom, producing two particles. The most common pair production is of electron and positron. As energy must be conserved for pair production to occur, the incoming energy of the photon must be above a threshold of at least the total rest mass energy of the two particles created. Neutrino-electron scattering is a process where a neutrino scatters off an electron by the exchange of a Z0 boson.